Welcome to our presentation on the research paper entitled HorseNet, the novel deep learning approach for horse health classification. This research, in fact, addresses the critical need for accurate, efficient, and non-invasive approaches to assess the horse well-being. I am Dr. Nesreen Atidallah from the Faculty of Computer Studies, Arab Open University in KSA, and I will present as the first author in this paper the research in this paper. So let's start by some introduction. In fact, the surveillance of animal health, especially in horses, is of almost importance in guaranteeing their welfare, their productivity, and economic significance in both professional and leisure contexts. Conventional or traditional approaches to monitor the horse health often include labor-intensive subsection and time-consuming manual observation and assessment conducted by veterinarian in these tasks. So there are numerous inherent limitations associated with traditional techniques for monitoring the health of horses. Initially, it is important to note that the process of manually observing and evaluating the health of horses by veterinarian uh, by, veterinarian is time consuming. Also, these issues emphasize the need for new methodologies that may effectively tackle these limits and enhance the precision and the efficiency of horse health monitoring. So the use of cutting-edge technology such as artificial intelligence, machine learning, and wearable sensors, and let's say computer vision models present novel prospects for the automation and for the enhancement of animal health monitoring, and hence enabling a more complete and a non-intrusive approach to evaluate the animal well-being. So, through the adoption of novel approaches, it's possible to augment the well-being, efficacy, and economic worth of horses, guaranteeing their sustained prosperity in both leisure and occupational context. Now, after literature review of the related works in the surveillance of animals, as well as in the use of these new and emerging technologies, we reveal or we perceive that the use of recent advancement in machine learning and deep learning have significantly impacted animal health monitoring across various species. So we found some works dealing with machine learning algorithms that are applied to predict health issues by analyzing feeding behaviors. Also, wildlife conservation efforts have benefit from transfer learning, which has improved animal identification in images. In the poultry also industry, support vector machine and artificial neural network have demonstrated high accuracy in detecting avian diseases. So, as you see, there is some good results in the use of these recent approaches to detect and to classify the monitoring of and to help in the monitoring of animals. But despite these advancement, the field faces challenges such as the limited data sets, such as the need for standardization across different studies and applications, and the development of user-friendly tools to make these technology more accessible to animal care professionals. So addressing these challenges will be crucial for the continued growth and effectiveness of any AI-driven animal health monitoring systems. This is the key problems, and this is the motivation behind our research, is the difficulty in early detection of health issues in horses, and the need for efficient and accurate diagnostic tools. So we suggest using the deep learning to improve this detection and these diagnosis, okay, by using smart classification. Now, the main contributions of our research is, first of all, is a comprehensive data set called HorseNet 1.0 that contains horse wellness images capturing diverse situations and circumstances, and validated and reviewed by specialists, by experts, to ensure the reliability and the accuracy of the data. After that, an efficient deep learning approach for rapid and accurate detection and classification of the horse wellness was applied, and the performance evaluation of this approach were implemented, and the assessment of multiple deep learning models, such as the VGG16, the Inception version 3, and the proposed convolutional neural networks using the novel data and the novel data set was implemented. So let's start by the first contribution in our paper, which is the study, which is the data collection. So this study, in fact, presents an innovative methodology for the identification of horse health status via the use of deep learning. And this study introduced several key innovations in the horse health monitoring. Now, the study was conducted at the esteemed Horse Club located in Ahsa, in a region known for its rich equestrian culture in Case A. And during the initial stages of this research, the authors, we encountered a challenge in finding a suitable dataset that adequately represented the diverse range of horses and conditions relevant to our study. So the collected images were specifically sourced from this horse club situated in the Ahsa, and by actively engaging with these horse club and obtaining their cooperation, we are able to acquire a diverse and representative data set that formed the foundation of this research. So the total number of images we have collected was 1,218, classified into two categories, into two classes. Class 0 for normal horses contains 478 samples, and the class 1 for abnormal horses that contains 740 samples. Also, during this research, we use deep learning models. Now, we focus on the convolutional neural networks, and why we can ask why, especially convolutional neural networks. In fact, it is well suited for image classification and well used in the computer vision classification. Also, transfer learning involves leveraging a model pre-trained on problem to solve different problem. So this approach will gain traction in the realm of the deep neural network, given their substantial data and computational demands. So this transfer learning allows for a more efficient training process by refining a previously trained deep learning model for a similar task. So we will have faster training, we will require less data, and we will achieve a good performance with the limited resources. So this is why we will use a transfer learning model, and especially the VGG16, which is known for deep architecture, and the Inception version 3, which is known with its depth and multi-level structure to capture the wide image complexities. So during this approach, so approach, the proposed classification framework entails a well-defined workflow comprising 5 key steps, which are: we will start by gathering data, refining and augmenting this data. And after that, we will employ various models, deep learning models, such as the classical or the proposed, the built-in layers, multi-layers convolutional neural networks, and the transfer and fine-tuning the pre-trained transfer learning models, VGG16 and the Inception version 3. So this, in fact, it is a critical phase in any computer vision system. It will involve the pre-processing of the images. So we have in the first pre-processing the images. Initially, every image was resized to dimensions of 300 by 300 to ensure square-shaped images. And after that, these images were altered to match the input dimensions of various models. So for the custom designed HorseNet, the images were adjusted in the first 256 multiplied by 256 pixels, and for the VGG16 and traditional the proposed convolutional neural networks, they were changed to 224 multiplied by 224 pixels. Meanwhile, the input for the Inception was resized to 71 multiplied by 71 pixels. So these deep learning models typically need a vast amount of data for optimal performance when there is a limited training data. So we use image augmentation to produce more images for the training as well as for the testing. And we will use many techniques in this augmentation, like rotation, noise addition, shifting, mirroring, blurring. So from the initial data set that consists of 1,218 images, after augmentation, we reach more than 24,277 images, which was split into training, validation, and testing. So amongst these models, we evaluate the performance metrics for these 3 models. We evaluate the accuracy, the precision, the recall, and the F1 score. And as you can see, we can see the accuracy and the loss, the smooth train and accuracy validation for the validation, the training, during the training for the 3 models. And also we compute the confusion matrix for the 3 models. And as you see here, we have the Inception version 3 outperformance. In fact, amongst these models, the Inception version 3 stands out with commendable accuracy, precision, and recall rate, each at 97%. And this is tailed by VGG16 and subsequently the proposed CNN. So overall, the models grounded in transfer learning showcases robust performance, boasting an accuracy surpassing 95%. Inception version 3 emerges as the top performer with all metrics at or near 97%. And this indicates not only high accuracy, but also a balanced capability in precision, recall, and suggesting few false positives and false negatives. And this balance is crucial in medical or wellness contexts where both types of error can carry significant consequences. So this is the results of our models, and as the study impact and the future directions. So we are aware that our research represents a potential to revolutionize preventive care in horse welfare and combines the novel dataset with a smart early detection for the horse for the horses wellness. Okay, and as a future directions, we need to expand our dataset to have more and with the breeds, with ages, more conditions, more locations also, to get more insights and relevant informations and relevant accuracy in this field. So as a conclusion for this research, this study examined the use of deep learning algorithms, particularly the inception, the transfer learning, and the convolutional neural networks, which to monitor the horse health and identify, classify the normal and abnormal behaviors. So we use the well-chosen dataset from the horse clubs with a variety of breeds and health concerns. Pre-trained Inception version 3 surpasses convolutional neural network and other pre-trained models with an accuracy of over 97%. So the study showed the benefits of transfer learning with the pre-trained models. Working with and training these models is easier since they remember past learning activities. As the future works could expand upon this work by incorporating larger datasets and refining the deep learning techniques for enhance the treatment and the management of the horse health. Additionally, applying these models in practical scenarios hold considerable promise, and this would entail integrating these algorithms and models into the veterinary diagnostic frameworks and evaluating their efficacy based on tangible clinical results. So let's move now to have an overview about the implementation. So in fact, in the implementation, we need to create we need to create the augmentation, so we can use the TensorFlow and the image data generator to have more images, to create more images with different range, with different rotation, with different zooming, etc. After that, we need to load the data. After loading the data, so we need to, for the proposed CNN, we have many layers that are superposed, okay, in some orders, in order to to the good classification for our for our sets. Okay, we can save our model, the checkpoints of our models, to open it later if you miss any results. So after fitting your model, you will have the loss and the validation and the accuracy. You can pre-train after that your model to have the accuracy, and you can see here we have 90% accuracy for the convolutional neural networks, and this is the confusion matrix. It's again, we can also draw the smooth terrain accuracy and validation accuracy, as well as the terrain loss and validation loss, okay, and the curve also for the false positive rates and true positive rates. For after that, we will move to the inception. So we need to reshape the image size. Again, we will load our data set. We will call the pre-trained inception version 3, and after that, after some freezing and adding new layers for classification and training, we will get again the performance of our inception. So this is the best performance, and we can see here that we get 96.92%. So it is almost 97. This is the confusion matrix. So for the VGG16, again, it's the same. We need to load, firstly, we need to load all the libraries. We need to load after that the data sets and reshape the data set to the image size, as we explained before. Now we need to call the pre-trained VGG16, the transfer learning, add some layers, and the correct layer, the sigmoid for the binary classification. And after that, define the metrics and fit the model. After training, you will get your loss and your validation. Okay, so this is the performance of our pre-trained VGG16. And as you can see here, we have 96.18. So 96, it's the accuracy for our VGG16 model. Okay. So this is the accuracy, it's almost 96, okay? And we can see easily that the Inception version 6 outperform all the other used deep learning models. Okay, so this is the end of this presentation. Thank you very much for your consideration, and I appreciate your efforts in conducting the very outstanding research level. Thank you very much.